A common strategy for solving a lot of programming problems is to first solve a stripped-down simpler version of them and then think what needs to be changed to achieve the original goal. Our first approach to this problem is also based on this very idea. So instead of thinking about the zigzag pattern of printing for the diagonals, let's say the program statement simply asks us to print out the contents of the matrix, one diagonal after the other diagonal, starting from the first element. So let's see what this program would look like. The first row and the last column in this problem would serve as the starting point for the corresponding diagonal. Given an element inside a diagonal, let's say I and j, we can either go up the diagonal by going one row up and one column ahead, for example, I minus 1 and j plus 1, or we can go down the diagonal by going one row down and one column to the left, for example, I plus 1 and j minus 1. Which way should we choose? Note that this applies to the diagonals that go from right to left only, but what if we want to go from left to right? Then the math would be changed. First, let's initialize a result array that will eventually return, and we have n rows and m columns. These variables to keep track of the size of the matrix. We would have an outer loop that will go over each of the diagonals one by one. The elements in the right row and in the last column would actually be the heads of the corresponding diagonal. We have to go over all the elements in the first row and the last column to cover all possible diagonals. So we need to figure out the head of the diagonal. The elements in the first row and the last columns are the respective heads. Then we have an inner while loop that iterates over all the elements in the diagonal. We can calculate the number of elements in the corresponding diagonal by doing some math, but we can just simply iterate until one of the indices goes out of the bounds. It iterates until one of the indices goes out of the scope. We just take note of index math and to go down the diagonal. First, we have n is the length of the matrix and m is the length of the first row in the matrix. So n represents how many rows in the matrix and m represents how many columns in the matrix. And then we declare a pointer d. It's start from 0 and it moves from left to right. So they will meet a lot of number like 1, 2, 3, 4, 5. But when d is equal to n, it's out of the row. Note that the last element in the first row is n minus 1. Then we should do a quarter turn. D move from top to bottom. So it is 10, 15, 20. We declare R for rows and C for columns to represent abscissa and ordinate. When we are in the first row, means if d is less than m, then the R is always 0, is a constant, and R and C is 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. So we can infer R is 0 and C is equal to D. Let's quarter turn to the last column situation. If D is greater than M, starting at D is M. When D is M, especially in this case, M is 5, and so D is 5 at the number 10. Let's keep moving on from top to the bottom, and we should notice when D is n plus m minus 1 is out of the boundary. So the last element of the last column is n plus m minus 2. And for the last column situation, it is if D is greater or equal to m, so the R and C is 1, 4, 2, 4, 3, 4. And you can notice C is always 4, it is a constant, and we can deduce R is equal to D minus C, and because C is m minus 1, so R is finally is equal to C minus m plus 1. So this is how the algorithm works, and we can loop them in the positive order. Let's say we have R and C, R for row and C for column. So in the upper right corner, the abscissa and ordinate is R minus 1 and C plus 1, and in the lower left corner, the abscissa and ordinate is R plus 1 and C minus 1, and blah blah blah, until we meet R is n minus 1 and C is 0. If R is n and C is negative 1, then we are out of the boundary. So let's set the scope. The C is bigger than negative 1, and I is less than n. This is our boundary. For each diagonal, we will need a new list or a dynamic array-like data structure since we don't know what size need to allocate. Again, we can do some math and calculate the size of that particular diagonal and allocate memory, but it is not necessary for this explanation. This is a simple problem to solve, right? The only difference between this one and the original problem is that some of the diagonals are not printed in the right order. That's all we need to do is to fix to get the right solution. Before we add this element to the final result array, we just simply need to reverse the odd number diagonal. So for example, the third diagonal starting from the left would be 3, 7, 11, and before we add this element to our final result array, we simply reverse them to 11, 7, 3. And for the odd number diagonal, we just add the element into our intermediary array. Then we directly add them in a positive order to our final result array. But for the even number diagonal, we add the element in our intermediary array, and then we inverse the order to our final result array. And finally, remember, every time we start to process another diagonal, we need to clear the intermediate array. Let's try to implement the code in Python. First, we have to define n and m, and they are the represent the lengths, represent the rows and the columns. And the n is the length of the matrix, how many rows it has, and the m is the length of matrix at 0. It's the first. Is in the first row how many columns, how many elements in the first row, and we then can print out to check it. Yeah, it's a 4 and 5, right? In this case, and we have to declare an empty list result and the intermediate. Both of them is empty array. And then we need to define a d pointer for d in range. D is the boundary is n plus m minus 1. It's the first row and the last column, and the intermediate. So inside the for loop, they have a different situation. So if we are in the first row, then d is less than m. Is how many columns we have. So i's don't change. The row, this is don't change, right? The I is always 0, and the c is d. C is always equal to d, and else I is d minus c, and c is m minus 1, and we then can print it out to check. Print d and r and c. Can print out to check. Yes, the d is always increment 1 by 1 by 1, and the c and r, when r in the first row, the r is don't change, and when c in the last row, the c don't change, just m minus 1. Cool, right? And we can comment out. Then we can use a while loop. While I is less than n, that means this is our inside loop. In every diagonal loop, we should keep them in the boundary. They are let the element don't run out the row and the column boundary. So the intermediate will append the matrix element r, and the c is the opposite coordinate and ordinate, and we can print them out to make a test. Oh no, we should first increment increment by 1. R increments by 1 because we move from the top to bottom. C is a minus, always the increment by 1. It's a move from right to left, and then we can print it out, R and C and matrix. Yeah, so this is all our elements of Caesar, how they in the order, but the order is a little different from the which we want. So we can first we comment out, and we need to I finish the first part. Then our last part is to judge if D is order, if D sequence is even, then is modular 2 remain 0. Then result extend intermediate is in reverse. But if else, if it is odd, we just extend it without change intermediate directly to the result, and we can print the intermediate. So this is how it always how it add to our how the intermediate add to our final result. And we can return our result. Oh, this happened because we didn't clear. So first, before the list, we need to clean our intermediate dot clear. We need to always clear, so make it works. And or before the function, we need to consider the edge case. If it is empty, if not matrix or not matrix at 0, that means it is an empty list. Then we return empty. So we did it. This is how it works. It's a bit hard, right? Let's analyze the complexity. The time complexity is O of n multiply n. Considering the array has n rows and m columns, an important thing to remember is that for all odd number diagonals, we will be processing the element twice, since we have to reverse the elements before adding them to the result array. And additionally, to save space, we have to clear the intermediate array before we process a new diagonal. That operation also takes O of k, where k is the size of that array, so we will be processing all the elements of the array at least twice. But as far as the asymptotic complexity is concerned, it remains the same. And the space complexity is O of minimal n and m. Since extra space is occupied by the intermediate array, we use it for storing diagonal element, and we maximize it which can occupy, so it is equal to the minimum of n and m. Remember that the diagonal can only extend till one of its indices goes out of the scope. The next approach I'm going to talk about is simply and plainly. It will do what the program statement asks us to do. It is pure simulation. However, in order to implement this simulation, we need to understand the working patterns inside the array. Basically, in the previous approach, figuring out the head of the diagonal was pretty easy. But in this case, it won't be that easy. We need to figure out two things for each diagonal. The two things are the direction in which we want to process its element and the head of starting point for the diagonal depending upon its direction. The arrows as I draw represent the direction of the processing of each diagonal, and the colored cells as I marked are the corresponding head for each of the diagonal, is corresponding to the direction in which we need to process them. Now that we know what two things we need to figure out, let's go to the part where we actually do it. The direction is pretty straightforward. We can simply use a Boolean variable and keep alternating it to figure out the direction for a diagonal, and that part is sorted. But the slight tricky part is to figuring out the head of the next diagonal. The good part is we already know the end of the previous diagonal, and we can use that information to figure out the head of next diagonal. Let's look at two scenarios that we may come across when we are at the tail end of the downwards diagonal and we want to find the head of next diagonal. Let's say we are processing the diagonal 2 to 6. When we are at 6, the head for next diagonal will be 11, and that's the node directly below the 6. When we are processing the diagonal 4, 8, 12, and 16, the head for next diagonal is 17. This is the node to the right of 16. So when next head is going up, the general rule that we will be following when we want to find the head for upwards going diagonal is that the head would be the node directly below the tail of the previous diagonal, unless the tail lies the last row of the matrix, in which case the head would be the node right next to the tail. Let's look at the two scenarios that we may come across when we are at the tail end of an upward diagonal and we want to find the head of the next diagonal. When we are processing the diagonal 11, 7, and 3, the head for next diagonal is 4, and this is the node of the right of 3. When we are processing the diagonal 17, 13, 9, and 5, the head for next diagonal will be 10, and that's the node directly below the 5. So next head when going down, the general rules that we will following when we want to find the head for a downward going diagonal is that the head would be the node to the right of the tail of the previous diagonal, unless the tail lies in the last column of the matrix, in which case the head would be the node directly below the tail. So the algorithm is working like this. First, we initialize a Boolean variable called direction, which will tell us whether the current diagonal is an upwards going or downwards going. And based on the current direction and the tail, we will determine the head of next diagonal. And initially, the direction will be 1, which would indicate up, and we will keep alternating the value from one iteration to the next. Assuming we know the head of a diagonal, let's say matrix at I and j, we will use the direction to process along the diagonal and process its element. For an upwards going diagonal, the next element in the diagonal would be matrix at I minus 1 and j plus 1, and for a downwards going diagonal, the next element would be the matrix at I plus 1 and j minus 1, and we keep processing the element of current diagonal until we go out of the boundary of the matrix. Now, given that we know the tail of the diagonal, the last node before we went out the bound, let's see how we can find the next head. The direction is for the current diagonal, and we are trying to find the head of next diagonal. So if the direction is up, it means the next diagonal would be going down and vice versa. We keep processing the element of a diagonal, and once the current diagonal ends, we use the current direction and the tail element to find the next head and switch over the processing to the next diagonal, and also remember to flip the direction bit. Let's implement the algorithm in Python. First, as we notice, we have an example as our input matrix to show how it works, and the first thing we need to do is to consider the edge case to check if it is empty, if it is nothing, by if no node matrix or node matrix at 0, the first row of the matrix, then we just return empty. It just returns an empty list. And after we consider the edge case, we can define the dimension of the matrix, as we can say n and m. The two variables represent the length of the matrix, and the length of the matrix at the 0 index. That means it is a 0 line, and then we have indices that will help us to progress through the matrix. Is variable r and c. They all of them start from 0. They will iterate. All of them is start from 0. that's the element of time. To every time we just progress one element at a time, and we have a d for direction. This variable will help us to keep track what direction we are going to process the current diagonal. Whether it is actually it is a Boolean variable. It's a 1 for true or 0 for false, and then we have a result. Result is an empty array that will contain all of the elements of the result to return the final result we need to return to from our matrix. And then we need to let's start. First thing we need to do is build a while. We need to set the boundary. The while loop that will iterate over all the elements inside the array that are is less than n is the boundary. So it can be n because n is beyond. So the matrix, the maximum of the row is n minus 1, and the maximum of the c is m. So they can't beyond the boundary. So if they beyond the boundary, we just stop the program. So first and foremost, the current element we need to do is to add the current element to the result array. This is most critical. This is what we want to get from our result dot append. So every time it will append to add a new element, c. So r and c for row and column is this time is become our abscissa ordinate, and we can move along in the current diagonal. How can we move along the elements in the current diagonal? It depends on the current direction. So we can use two new variable, new r and new c to hold our result, to hold our new head. So if the d is 1, we only consider if the d is 1 because d only have two possible, either it's a 1 for true or 0 for false. Then that's when the d is 1, that is true. Then the diagonal is going up, and so this time r is minus c and I is minus 1 and c is plus 1. So r plus I is increment. Or I is a decrement by 1 if it is upward, or else it is increment by 1. So c plus is vice versa. So if it is one that we are going to right upward, so c is a plus, and else is another way. If it is to the left lower column, we just decrement by 1. Else. So we then need to check if the next element in our diagonal is within our boundary of the matrix or not. If it is not within boundary, we have to find the next head. If the new r is less than 0 out of the boundary, or new r is equal to n out of the boundary, we only consider if it is on our boundary. When it is on our boundary, it's also out of our boundary, right? Or new c is less than 0, or new c is m. And then we can so then we need to use the d to determine the direction. If d is true, it means when d is 1. If the d is 1, the current diagonal will going upward to the direction. So in that situation, so it will going up, and we have r and c as in the tail. The r R and C, only the C is increment, so will increment by 1. So if it is in the boundary, so R is increment if the C is on the last column m minus 1, so it will become next head. Otherwise, the element is directly below. So otherwise the element is directly below. The element will be C increment, and R will be the next head. So C is increment by 1 if the C is less than m. So if C is less than m, we just increment by 1. If not, it's increment by 0. And we can consider another situation is else. Else is for downwards going. If our diagonal is going downwards, the R and C, only the C is increment. If it is within the boundary, then it will become a next head. So otherwise, the elements will below the element will directly choose the below the element, so will become R decrement by 1. So C increment if the R is n minus 1, and R decrement if the R is less than n minus 1. And then after we finish, we need to flip the direction. So D is flipped to, if D is 1, next time it will become 0. If Z is 0, next time will become 1. So true false, and like a flip a coin something. And else means we just use the next R and next C for our next header, and we can finish. We can just return the result. Yeah, that's how it works. It loops. Let's analyze its complexity. Since we process each element of matrix exactly once, so the time complexity is O of n multiply n. And since we don't make use of any additional data structure, so the space complexity is O of 1. Note that space occupied by output array doesn't account toward the space complexity, and since that is the requirement of the program itself, so the space complexity comprises any additional space that we may use to build the final array. For the previous solution, it was the intermediate array, but in this solution, we don't have any additional space apart from a couple of variables.